The machine that you just saw is called a Dyna Flux alternator. I invented that many years ago in northern Michigan when I was working for Bethlehem Steel. And the story behind its evolution is pretty interesting, but we'll forego that to another time. More importantly, I think I'll concentrate on what the device actually does. In order to give you some insights into that, what I'm going to do is give you a really simple but effective demonstration about why electricity costs so much to produce. This is a samarium cobalt magnet. There's absolutely nothing unusual about it except for the fact that it's extremely powerful. If I drop this, it falls in the gravitational field just like any other object would. That's the whole purpose of showing you it separately so you can see how fast it falls. This is a brass pipe. Now, when I drop this into the brass pipe, you might expect the same results, but believe me, it'll be very different. Because it's going to take a great deal of time for that thing to transit the pipe. Now the question is, why does that happen? See how long it takes as opposed to when I drop it in the open? The reason for that is that as this magnet moves through the pipe, its motion and its magnetic field create currents inside the material of this pipe. And those currents in turn produce a magnetic field of their own. And that magnetic field bucks the progress of the magnet, so that instead of accelerating at 32 feet per second, it just falls at a constant velocity. Well, the exact same thing happens in an electrical generator, except that the effects are a lot more expensive. Let me just get an armature for you to look at. This is a standard armature removed from the kind of generator that you might have being turned by a gasoline engine or a little diesel engine, something like that, so for auxiliary power in your home, for instance. You'll notice that there are coils embedded in the material here. And as this rotates through a magnetic field, there's a voltage produced in these windings. That's in concert with Lenz's law. But also, what happens is the minute you close the breaker and take current out of this device, forces appear which attempt to cause this to motor or to twist as a motor in a direction opposite to that which you are attempting to turn it. And so the prime mover, your gasoline motor or whatever it is you're running this with, then has to labor to overcome this back torque or this reverse torque in order to continue this thing turning at a sufficient speed to give you the voltage that you need to keep the current flowing. In very simplified terms, that actually is the reason why it takes so much power to turn a generator. Or, to put it in more succinct terms, the power in has to equal the power out. There isn't any advantage that you can seek which will increase the overall efficiency or reduce the amount of fuel that you're consuming. But that's only true of this particular geometry. Now I'll demonstrate a different approach. You noticed in the previous piece of equipment that I showed you, the shape was cylindrical. If you focus on this machine, you'll see that we're making use of a very unusual geometry in the rotor. It's actually an ellipse. It's an ellipse in 3D, but the cross-section of that ellipse is still circular or cylindrical, and so it can rotate between two field poles without any difficulty. Now there's a very specific reason for doing this. When we create a magnetic field with this winding, the flux comes down through here, attempts to cross over to the other side and return to the magnetic coil, and this is the only path that it can take to do that. So when this is rotating, the net result is that the flux in both of these pole pieces is actually oscillating back and forth. And when it oscillates back and forth, it's moving in a direction which is 90 degrees away from the direction that is used in a standard generator to produce a voltage. So it's actually shuffling back and forth horizontally in these pole pieces and creating a voltage in these windings. And then when we close the breaker and attempt to use that current, the result is that for part of the cycle, it's going to be experiencing a resistance to motion, and for the other part of the cycle, it's actually going to be experiencing an assistance to its turning. And as a result of that, we wind up with a totally different concept in generation and very different numbers to describe the efficiency of the system. It's a very long and laborious presentation to go through all of the numbers because it requires a thing called a segregated load analysis, which I think the audience would find very boring. However, so this last machine is also a DC motor. It's a very different one from the others I've shown you, it's a reluctance motor with a rotating field, and the field is produced by an external switching device or circuit controller, as we call it. This circuit controller is electromechanical. It's actually motor driven. But ultimately, if we can get the funding, I will replace this by a totally electronic device which then incorporates the recapture features and all of the normal things that you would have a computer do to optimize a motor. And that will allow us to get unheard of efficiencies out of this device. But in its present state, what I can demonstrate, which is pretty interesting, is the fact that you actually can produce a constant torque over a fairly large speed range. What's going to happen if we go too fast with this thing is that it does get out of sync with the controller, in which case the motor loses its orientation. But anywhere from about 0 RPM up to almost 500 RPM, this thing is very predictable and very linear. Our studies have demonstrated that with the proper electronic controller and the necessary embedded processors, we could probably take this up to 10,000 RPM and still demonstrate the same characteristics. So with that, let me switch on the power and give you a quick demonstration. Now, one of the things you'll notice when I turn on the power is that this rotor will jump to its null position, which is going to be an exact imitation of the position of the controller. And these two things always turn in synchronism under normal conditions. So let me get this turned on. And there she turned. Now, believe it or not, we have full torque right now on this motor. I mean, if we had the equipment hooked up, I could demonstrate that to you with meters, but I just measured it the other day for some folks who were here, and it's 54 inch-pounds of torque. So that's a pretty impressive number. And we're only pulling 2.28 amps on both our power windings. So that's a pretty significant amount of torque considering the investment of current. Now, as I turn up the speed, you'll notice that these two guys turn together in synchronism. and the torque is just as frisky as it was before. I can't stop it, and this shaft here is about 2 inches in diameter. Actually, if we applied a pony brake to the larger diameter of the pulley, you probably could seize it, but it would be it'd still be difficult to do. Well, I'm accelerating it manually. We still have that same frisky torque with no real problems. And if I lower the speed, it stays in sync with the transmitter or the controller. Well, this, out of all the machines that we showed you today, this is probably the one which is closest to commercialization. What we need right now is enough funding to finish the design of the electronic controller and probably build another prototype as well. But anyway, that's what's on the agenda, and these are the types of things I've invested most of my life in perfecting. The other equipment that you see in this room represent other technologies, which are just as interesting, but they're a little bit more obtuse than what I've showed you so far. We only